Hey everyone, welcome into this lecture number 7 of the semester on graphs and models. This corresponds to section 10.1 of Rosen's text. So this lecture is going to be a little bit shorter. This section of the book is full of examples, and I'd like you to read those examples, but I'm going to start by just going through some definitions and then looking at some examples with you, but I'm going to leave most of the examples for you guys to read through. So number 1, let's just talk about the definition of a graph. So I think we know basically what a graph is, but it's very similar to a digraph. So a digraph we're going to see again in this section is a special example of a graph. A more general definition is the following. So I'll just start writing. A graph is a double. So we'll call the entire double G, and it consists of two sets, V and E. These are the vertices and the edges that we're used to. So the vertices, V, and edges, E. All right, and each edge has either one or two vertices. So this is a little bit different than a digraph, at least the way that it's stated here. But this is the way we're going to define a general graph. So each edge has one or two vertices called its endpoints. And notice that in this scenario, the order of the vertices is not specified. So it's possible that this could be undirected, in other words, right? And so the basic idea here is that edges connect endpoints. And that's the whole idea of a graph. So edges connect endpoints. There are a couple of other definitions that we want to make here. One of them is the following. So if the cardinality of V, of the vertex set, is equal to infinity, then we call G an infinite graph. And otherwise, it's going to be called a finite graph. All right. So an infinite graph has infinitely many vertices. So when we say an infinite graph, that's what we're referring to, the number of vertices. And then obviously, likewise, I'll just write this down, but this is what I just said. If the cardinality of the vertex set is less than infinity, then G is a finite graph, which makes sense, right? That's what it should be, because that means the cardinality of the vertex set is finite. There's finitely many vertices. Okay, it is obviously possible that a finite graph could have infinitely many edges, and we will maybe see an example of that as we move forward in the class. But in general, those are not going to be useful, because if you have a finite number of they're useful. Okay, I shouldn't have said that, but we're not going to study them too much, because if you have finitely many vertices, and you somehow had infinitely many edges, then it means, just think about the pigeonhole principle. It means that eventually some of those edges would become superfluous. You wouldn't need them all, right, to be able to at least connect the vertices that are supposed to be connected. Remember, if that's the job of the edges, to connect the vertices, then you wouldn't need all of those edges if there's infinitely many of them, right? Some of them would be repeats. Many of them would be repeats, right? There's another definition here. So a pseudograph is a graph that could contain loops and possibly multiple edges connecting the same pair of vertices, all right? So this is kind of what I was just talking about. Another name for this is called a pseudo. So this is a name, okay? So a pseudograph sometimes is just called a graph still, though, but a pseudograph is another name, I'll write it this way, used for a graph that may include loops. And by loops, I mean vertices with one edges with one vertex to just connect the same vertex to itself. So it could contain a whole lot of loops, right? Could contain loops and possibly many edges connecting the same pair of vertices. And by many, I usually mean more than two. All right. So we know that in a digraph, order matters, right? So then there can be two different edges that connect the same pair of vertices, but they're different because the order matters. Same pair of vertices. All right, so let's look at some examples. Let's start. So I've got these examples saved down here. Let's start with this one. It's supposed to represent a computer network. And scroll up and put it up here in the notes. So this is a computer network. We're going to build on this graph. So right now, this is supposed to represent a national computer network where each of these cities has a single hub for a computer, and the edges can connect these cities that are connected by this hub, okay, or by this network, I should say. So San Francisco is connected to Denver, Denver's connected to LA, San Francisco's connected to LA. They form a little triangle here, right? Denver is connected to Chicago, so you could get from San Francisco to Chicago through Denver. You'd have to route your information through Denver, but there is not an edge that just connects San Francisco to Chicago itself. All right, so this is the idea. So this right here is a graph that has 7 vertices, and then however many edges. So I didn't count them, but 4, 5, 6, 7, 8, 9 edges that connect them. But the idea here is that these edges have the vertices, pairs of vertices have only one edge connecting them, right? So this is perfectly fine. But it's possible that in your network you could have 2 different modes connecting these, and these pictures are all in the book, okay? But you could have 2 edges per pair here, and they could represent, incoming and outgoing information or something similar. And at this point, if you do want, so this is another graph, right? This is a graph with twice as many edges, but the same number of vertices, and actually the exact same vertices. And one way to interpret this, again, is to consider that, these edges represent one-way traffic of information in the network, right? So for example, the straight edges could represent, working from right to left somehow, right? The flow of information from left to right, I should say, on your screen. Left to right. And then the other edges, the kind of curved ones that I just drew, those could represent the information flowing backwards in the other direction. And so what I've just done is I've turned this graph into a digraph because I've added information here. So this is digraphs, of course, are examples of graphs. And these are examples of graphs that have more information actually. Because in a digraph, as we remember, the direction matters, right? So an edge, say E1, if E1 is an edge that connects vertices V1 and V2, in a normal graph, if you had another edge, E2, which is like V2, V1, these would just be straight lines that connect those 2 vertices, and the order doesn't matter. But in a digraph, these do matter, right? So order matters in a digraph. And the reason, how do you remember that? Order matters. Well, di means direction, right? So the direction matters in a digraph. Hence the name. All right. Now it's also possible, so the example in the book, it talks about computer networks and all the different kinds of computer networks that you could have. It's possible that, or you might want this, right? If you were setting up a computer network similar to this, you might want self loops for like diagnostic testing, where you could send sample packets of information and just make sure that everything's going through properly. And so each one of these hubs could have a self loop here, a little self loop where they do their diagnostic testing, just sending information to themselves. So this graph is getting a little complicated here, right? But it's still not that crazy. There's only seven nodes or 7 vertices, and we've added a whole bunch of edges. So we started with 7 edges or 8 edges? There's 5, 6, 7, 8, 9. There are 9 edges, right? And so then we added 7 more for the loop, so that's 16, and then 9 more, so 25 total edges here. It's not super crazy. It's still pretty small as far as a graph goes. But it's a lot more complicated than what we started with, right? So, we're used to diagram. We remember the definition of diagram, so let's look at a couple other examples. Basically, this is all we've got in this lecture. It's going to be, like I said, pretty short. So I want you to look at the lecture or the examples in the book, but let's look at a few of them together. So this next one is called an acquaintance graph. Let me move it up. So these are just models of how you would build your graphs from like real life information, right? So here's our example 3 is going to be an acquaintance graph. And let's zoom in on this thing. It's going to stretch it out a little bit. This is good. So this graph right here just shows the, it just shows a whole bunch of people, right? And they're connected. So they're connected by edges if they are acquaintances of these other people, right? So, for example, Amy here has a whole lot of acquaintances. Amy's acquaintances with Todd, Steve, Liz, Paula, and then in turn, Paula has a whole bunch of nodes as well, or edges as well, emanating from their point. But over here we have like Kamlesh and Ching have only just one edge between them. Kamlesh also knows Todd. So all these people are interconnected, right? But some of them are more connected, right? They're more in the web than others. But this is an acquaintance graph. So you could try this. You could try this with your family. You could try this with, so example for you guys, try this. So try to draw an acquaintance graph for if you're living in the dorms. Try to draw an acquaintance graph for your hall or something like that. Just try to draw an acquaintance graph. Just pick out some people that you know. And obviously, if you draw the graph for yourself, you're probably going to have a whole lot of edges emanating from you, but you might have groups of acquaintances or friends that are not connected to each other than through you, right? Other than through you. So an acquaintance graph is a model to kind of show, friendships or acquaintances. You could do it on campus. You could do it from your work. You could have your work groups, your school groups, family groups, etc. But I recommend that you try to draw an acquaintance graph with at least 10 people or something. Just see how well it goes from there. All right, let's look at the next one. So there's not much to say about these. It's just a matter of taking a look at them. Here's an influence graph, I should say. So this one is named influence graph. So the idea is that this is an acquaintance graph kind of kicked up a notch, right? So this is not just people that know each other or are acquainted with each other, but now they influence one another. So in this case now the arrow, so if you have two people, so person 1 and person 2, the edge means that they're acquainted, so they know each other, they're acquainted with each other, and then there's an arrow between them, and the arrow tells you that the one person is influencing the other person, right? So in this sense, P1 has some influence over P2. So maybe if you draw your acquaintance graph and then you could add in some arrows, right? So what would the influence graph, what would be an example of this? Well, if you include your work group, like people that you work with, in your acquaintanceship graph, then an arrow would be like a boss or a manager or someone who's worked at the company, for a longer time and who you respect and has an influence over you. Influence can obviously come in many different forms, right? It can be artificial. It can be just, because of earned respect, whatever. So there can be influence in many different ways. And as you can see from this picture with Brian and Yvonne, people can influence each other. And actually, that's probably, we don't need to get into relationships here, but it's probably a good symbiotic relationship, right? That these two people influence each other. Down here, Deborah has a whole lot of influence on others, but there's no one influencing Deborah. Notice that. So if this was a company's flow chart of ideas or something, if all the ideas are coming from Deborah and none of them are coming in, then that's probably not a good balance either, right? So, but that's not really the point of this question, right? The example is just to show how one would draw an influence graph. So you could draw one of these you could take your acquaintanceship graph that you've just drawn, hopefully, and add some arrows to it and turn it into an influence graph. All right. So then I just have one more example here, and I'm going to then leave you guys to look at the rest of these in the text and think about some other examples maybe. This one is a single elimination tournament, and it makes me think of college basketball, March Madness, sometimes called. And it's this particular example is hurtful to me. We'll talk about why first of all. So the idea here is that each of these edges actually represent. So this is it's a little more interesting. I don't know about interesting. It's just it's a different graph, right? So it's a slightly different type of graph because the nodes and the edges. So the nodes represent actual games, okay, a single game, but each game is played between two teams. So in this case, Stanford and Georgia. And then you have to give a little key at the top. It could be anywhere, but a little key that tells you how to understand this, right? Because As it is itself, if you just draw the edges in the nodes, well, then you know that eventually somebody wins these games and moves on, and there's more games, right? One game leads to another. One game leads to another, and you could draw directions here to show where how the winning teams flow, and they both flow into this one, right? So this point right here is the final point, the final game of this tournament. But that's not enough information if you care about who played in the games, what teams played in the games, right? So you see Stanford, that's where the key comes in, right? So the winning teams are shown in blue. And the reason that this graph is so hurtful to me personally is because Connecticut, I grew up in Syracuse, New York, and I'm a huge Syracuse basketball fan. My siblings both went to Syracuse University, earned their degrees there, and so I just can't abide by Connecticut winning this championship, whatever tournament this was. But it's just an example, right? But still, what I'm going to do is change this out so I won't write it everywhere. But there we go. Swap out Connecticut for Syracuse. And now this is a wonderful example of a single elimination tournament. Again, if you want, you can add in, make this a digraph and show that the directions of all these edges are flowing toward this championship game, right? And so, all right, so these are just a few examples, 4 examples from the book. There are, I think, 14 examples of different models. They're all a little bit different, but they're all similar in the sense that you end up just drawing a graph. Some of the graphs are directed. Some of them are not directed. They're just regular graphs. Some of them have multiple edges emanating from each node. So there's some with phone numbers, some with programming with variables and precedence of variables that are set in a computer program. So I urge you to read these examples. You don't need to read every single word, but think about them. Most of them have pictures. Look at the pictures, make sure the pictures make sense, and then do the couple of exercises that I've listed here. And in the next lecture, we'll get into terminology, special types of graphs, and then some other properties and theorems about graphs. But really, this first section is just an introduction to graphs and models. So this is a short one. We'll leave this one here and be happy that it was a short one, because sometimes these run longer, so we'll enjoy the short ones when they happen. And I'll see you guys in the next lecture.